A ballistic pendulum is a device like the one pictured right here that can be used to measure the speed of a bullet. I've just kind of replicated this picture from the one on the homework, but just made it have one string instead of two. A block of mass big M is hung from the ceiling, and a bullet of mass little m is fired at the block. The bullet becomes embedded in the block, causing the block to swing upward to a height h, shown right here. And by measuring this height, a calculation can be performed to determine the original speed of the bullet. So first thing in part A, just describe the complete energy cycle for the process from when the bullet is fired from the gun up until when the bullet block combination reaches its maximum height. So the gunpowder in the gun is a form of chemical energy which is converted into the kinetic energy of the bullet as the bullet is fired. The bullet hits the block, which results in a release of some sound and thermal energy, but the remainder of that kinetic energy is converted into the kinetic energy of the bullet block system, which as it swings upward, that kinetic energy is just turned into gravitational energy. Now in parts B and C, we want to use conservation of energy and conservation of momentum to derive a formula for a couple different things. We want to express all the answers in terms of little m, big M, and the height h, and any physical constants. So in part B, use conservation of energy to derive a formula for the speed of the bullet block combination immediately after the bullet hits the block that would cause it to swing up to a height h. Now here's the important thing to understand with this question. We have a bullet hitting a block right here, which is conservation of momentum, because that's a collision. Then we have a bullet block system combined swinging from here up to here. That's going to use conservation of energy because we're turning kinetic energy into gravitational energy and there's no collision in this part. But what's important to note is that the final velocity in the conservation of momentum part, which is when the bullet hits the block, that becomes the initial velocity for the conservation of energy part. So once again to say that, the final velocity from conservation of momentum will become the initial velocity for the gravitational energy. Only that in this case, we're working the problem kind of backward because we know what this height is, so we can use this height to solve for that initial velocity, which is the velocity right after the bullet has hit the block. That initial velocity is the final velocity from the conservation of momentum part, because that's the velocity immediately after the bullet has hit the block. So we're going to first start in part B using conservation of energy to figure out what is this initial speed, the speed of the block immediately after it's been hit by the bullet and it starts to swing upward. So we're going to set up the conservation of energy equation. Ki plus Ui equals Kf plus Uf. Remember, we're just talking about from the bottom up to the top right here. So initially, does the block have kinetic energy? And this is where people make a mistake a lot because they say, well, the block's just hanging there, so it has no kinetic energy. What you have to remember is this is talking about immediately after the bullet has hit the block, but before the block has moved anywhere. So immediately after the bullet has hit the block, that has caused the block to have kinetic energy initially. But because this is the lowest point in its path, we're going to define that to be the 0 point of the gravitational energy. So we can just say that this term, the gravitational energy initially, is 0. And then when the block reaches its highest point, it's slowing down until it can't go any higher. And at that point, it has a kinetic energy of 0. So the final kinetic energy is 0, but it does have gravitational energy at that point because it's a certain height above its minimum. So using this equation, just have a couple formulas to plug in. The kinetic energy is 1/2 times. Now this is the combined mass. Remember, this is after the bullet has entered the block. So the total mass is m, big M plus little m, which I'll put in parentheses, times V initial squared. And that's equal to the final gravitational energy, which is same mass, big M plus little m, times g times h. Since the mass is the same in both cases, we can just cross it out, so it really doesn't matter what we even put down for the mass. And then what you're left with is just 1/2 vi squared equals gh. And we want to find a formula for the speed. So to get vi by itself, you're just going to multiply both sides by 2 to get rid of the 1/2. And the final answer, and then take the square root. So the final answer, vi, is equal to the square root of 2gh. That's all it is for part B. Part C, now we're going to solve the first part of the problem. This is the conservation of momentum part. So remember, the final velocity with the conservation of momentum of the bullet block system is going to be this initial velocity that we calculated from conservation of energy. So setting up conservation of momentum, we're going to have m1 v1 initial, that's the initial momentum of the bullet, plus m2 v2 initial, that's the initial momentum of the block, which, since it's just hanging there, is going to be 0, is equal to, now the bullet and the block are stuck together, so it's the combined momentum, big M plus little m, times v final. And we are trying to find the initial speed of the bullet, basically this vi, which is this v right here. So to get this vi by itself, we just need to divide both sides by m1, which is just mass of the bullet. So instead of calling this m1, let's just call it m, little m. So dividing both sides by little m, we now have a formula for vi, which is this whole thing. Remember, the one last thing is that this vf is actually this right here. So I'm going to plug that into this equation. So the final formula that I end up with is big M plus little m times the square root of 2gh divided by little m. And that would be your answer to part C. Part D is extremely easy. I'm going to let you do this one on your own. It's just a matter of taking all the numbers and just plugging them in to this formula to see if you get the answer that's given in the notes. The one thing you got to remember to watch out for is to convert the mass of the bullet, 5 grams, into kilograms, and also to convert the height that the block swings up to. That height of 4.5 centimeters, you're going to have to convert that into meters. So grams to kilograms, move the decimal 3 places. Centimeters to meters, move the decimal 1 place. And you should, move it 2 places, and you should end up with the answer that's printed on the homework sheet. If you're in AP Physics 1, you can stop the video here. If you're in AP Physics C, there's one more part to this question. This is part E, which says that some ballistic pendulums measure the maximum angle, theta, that the string makes with the vertical. So if we look back on the original picture, the angle theta is this angle right there. So if the angle theta is given instead of this height, we want to come up with a relationship that connects the height with this angle. And we also have to make the assumption that we know that the length of the string that's holding the block is L. And it's going to be L whether we're looking right here or right here. So what's the connection? What's the relationship between H and theta in terms of L? So I'm going to try to get H as a function of theta. So if I just redraw this picture down here and kind of blow it up a little bit. So this is when the string is vertical. This is when the string is slanted at its, where it says the maximum height. This angle is theta. The trick to this question is draw a horizontal line from right here over to right there. And the reason you can do that is because the height of the block, which is this part right here, that's your little h. That's the same as this h in the diagram. This side of the triangle, the hypotenuse of this right triangle, is L, but the whole side of the triangle, this L, is exactly the same as this from here all the way down to here. So if you treat from here down to here as big L, we can subtract off this H right here to get this side of the triangle. So that side of the triangle from here to here is L minus H. And now we can use a trig function on this angle because we know the adjacent side of this triangle, L minus H, and we know the hypotenuse of this triangle, which is L. So because we know the adjacent side and the hypotenuse, we can use the cosine function. Cosine of theta is equal to L minus H over L. If you're asked to find theta as a function of h, you would just take the inverse cosine on both sides. But typically what's done is you're given the theta and you have to find the h. So we want to get h as a function of theta. So I'm going to multiply both sides by L. So we have L cosine of theta is equal to L minus H. And then let's bring the H over to this side and the L cosine theta over to this side. That gives you H is equal to L minus L cosine theta. Or as is more commonly written, just factor out the L and you get H is equal to L times, in parentheses, 1 minus the cosine of theta. So that's your relationship that gives you H as a function of theta in terms of the L.